Hi, this is Duncan, and today we're going to be talking about math, my favorite subject. Have you ever been in a math class and just asked, why does this formula work? There's some numbers which it doesn't work. Just why? Why does this happen? The shy head nods I'm receiving through this virtual platform reassures me that you have all indeed thought critically about things that you've been told in math class. It's this critical thought and it's this idea of thinking critically about everything you're told, which brought about mathematics in general as a field. It also led to the formation of the form of mathematical proof, which is what I'll be demonstrating for you today. In order to properly convey any sort of mathematical idea, such as a proof, such as a theorem, any idea that you might have, you have to write a mathematical proof. In order to do so, you first got to believe your idea. You write out with a variety of examples, and then you attempt to generalize it. And then you write your idea in general terms as concisely and accurately as possible. So let's start with that first step. We're going to start out by trying to write out our idea with a variety of number sets. We're trying to understand what we're thinking of here. Let's say you want to test out adding two numbers together will give you even or odd. Then you'd have to look at an even number and an even number, of course. You'd have to look at an even number and an odd number. You'd have to look at an odd number and an odd number. Once you fully believe that it's just an even number and an even number, which give you an even number, or an odd number and an odd number, which give you an even number, from there, you can try to generalize. So make sure you believe your ideas and make sure you formulate them properly before we go into any other steps trying to generalize. So trying to generalize the numbers you just used. While you may think it works and you may believe it after a couple of examples with numbers that you've thought of, there's always other people who could think of other ideas just because of this critical thought. And maybe that's what your professors were trying to do from the start. So it doesn't truly prove just by giving an example. If you try all of your positive numbers, then you generalize your theorem to the set of natural numbers. Let's say all of the positive numbers that are whole, which don't include zero. Let's say that's where you want your domain of your proof to be. So you say at the beginning, well, let's say that this arbitrary element A is a natural number. If you need to use more than one, of course, you can allocate more than one, but just make sure that they are different letters for the variables. If during this step you find examples where the theorem doesn't work, feel free to generalize to other number sets, which might make it work in other scenarios. For example, let's have an even number and an even number. Adding them together, of course, gives an even number. But if you add just two natural numbers together, it doesn't necessarily show that the end product is always even. Let's say adding 2 and 3. Those are both natural numbers, but their sum is 5, which is odd. So let's say you've generalized it. You've generalized to the evens numbers and the odd numbers. Let's say you have to add 2 evens or 2 odds. Once you've successfully generalized it, you must write your proof out concisely and accurately. We usually define our numbers first. Let's say, for our example here, we let m and n be two natural numbers such that m and n are even. This is obviously vague enough. We have no idea what kind of numbers they could be. We just know that they're natural. And we know that they're even because that's what we said. Now, this is vague enough just not to be an example, so we know that the proof has begun. Now the tedious part begins. From your statement, you have to extrapolate more facts which lead to our conclusion. You have to keep in mind what you're trying to prove here, and you look at the information you have based on the number that you're giving. So for our example, we said that m and n are even. So we know that we can write m and n in terms of 2 times some other number, because every even number is divisible by 2. We do that, we say then n equals 2 times k, and m equals 2 times L for natural numbers k and L. Now we've generalized 2 more numbers here, k and L, but because they're non-specific, they're no specific examples, we can still do that and know that it's a formal proof. From there, you just have to stick to your mathematical guns and brute force algebra. keeping in mind what you want to prove, of course. We want to prove that the end result is even. So we want to look for 2 times some natural number, some integer. So we say that n plus m, we look at it, it's 2 times k plus 2 times l, which we know by simple addition rules is 2 times k plus l. Now that we know that k plus l is a number which classifies as a natural number due to natural number plus natural number, we can restate our theorem. If m and n are even numbers, then their sum is also even. Just based on the proof that we've given before, we know that we've successfully mathematically proven it. And the formality and rigor of the mathematical proof we just did, which is a really easy one actually, is what built up that acceptance of mathematical language, which we all speak to different degrees to this day. Your critical thoughts of your math teacher's knowledge is not unjustified. A lot of them don't provide these kind of proofs. This level of formally proving everything you're presented doesn't occur until very high-level mathematics. Keeping these proofs in mind, you shouldn't judge your math professors just based on, you shouldn't judge their intelligence based on the fact that they won't prove it to you. It's just a matter of not having enough time and too much material to cover. And through this rigor, we've built a complicated and yet understandable basis of mathematical knowledge. And it's from this which I enjoy studying to this day. Now, thank you and have a great rest of your day.